Crystal field theory. As in 1920s, valence bond theory is being developed and it is being very successfully running to know the geometry of the molecules. Though it is a very successful theory to estimate the structures of a given molecules, mostly of the organic molecules, but the valence bond theory is failed to give the definite structures of the transition metal complexes. To overcome this, the crystal field theory is being developed. Almost valence bond theory and crystal field theory, they developed in the same time period. Valence bond theory is failed to explain the colors, the different colors of the complexes given by the transition elements, and as well it is unable to distinguish the magnetic properties of the complexes. And as well, the valence bond theory is failed to explain some of the complexes, why the structure is octahedral or tetrahedral or square planar with respect to the number of electrons present in the d orbital. All these demerits of the valence bond theory are being concluded very clearly in the crystal field theory. And crystal field theory till today is very widely used in the estimation of complexes, d block elements complexes. And valence bond theory is very widely used till today for the organic complexes. So let's see what exactly the crystal field theory says. Crystal field theory is developed by von Welk and BTech in 1935. It is clearly mentioned and it has been accepted by wide range of scientists of that time. So the crystal field theory, why the name it has been coined? In crystal field theory, these scientists, they mention the metal and metal complexes surrounding metal surrounded by the ligands forming the metal complexes as the point charges, and most of the metal complexes are in crystalline in nature, so it is the name is being coined as the crystal field theory. In crystal field theory, the metal and the ligands are considered as the ions. The metal as a positive ion and the ligands surrounded by the metal to form a complex are negative ions or neutral ions. If the negative ions are present, then the electrostatic forces will retain the ligands to the metals. And when the neutral molecule or the atom is attached to the metal, then the negative dipole side of the neutral atom will attach to the metal ion. So it states that the metals and the ligands are firmly binded by the only electrostatic forces, and there is no overlapping of orbitals of the metal and to the ligands. No overlapping of the orbitals is been explained by the crystal field theory, but rather it is simply a electrostatic force. And as well as even the covalent nature of the metals to the ligands is not being mentioned, or it is not considered as the covalent nature of the metals. Then let's see the Salient features of crystal field theory. I'll write here as a CFT. CFT means crystal field theory. In crystal field theory, the metal and the ligands are considered to be point charges. That means the metal being a positive ion as a point charge, and the ligands may be negative ion or neutral point charge. Then likewise in the valence bond theory, here there is no overlapping of orbitals is being seen. So no overlapping means simply an electrostatic force. Electrostatic force is only the responsible force to form a complex. Okay, then all the d orbitals of the metal are degenerate orbitals. Like we know that dxy, dyz, dxz, dz square, dx square minus y square, all are degenerative in nature. That means all these 5 orbitals of the d orbital has same energy level. But when the ligand is been approaching towards the metal complex, the degeneracy of this d orbital will be lost and it will split into 2 categories. That is non-axial orbitals, and these 2 are axial orbitals. So when the ligand is approaching towards the central metal atom, if the central metal atom is coming through the axially, that means through the x, y or z planes, then that is called as the axial orbitals will be approached by the ligands. But when these ligands are approaching in between the axis, then they will come towards dxy, dyz and dzx. We will see clearly how these are going to be split. To understand how this degeneracy will be done, we have to know how these d orbitals are oriented in a cube. Let's see that. So in this way, the d orbitals will be oriented in a cube. These are the axial orbitals and these are non-axial orbitals. You can see this. This is a cube and dyz will be oriented. These orbitals are oriented in this way. You can see this. The x plane, the y plane and the z plane is the upper one. So the x and y plane, these orbitals are placed. We know the structure of d orbitals, that is double dumbbell structure, and the orbitals and the electrons are oriented in the same way. When you take the dzx, this will be the z plane, this will be the x plane, y, z plane. This is x plane, this is z, this is y. So these orbitals are oriented not along the axis but in between the axis in a x and z plane. And then dxy is oriented in this way. This is x, this is y, this is z. And these dxy orbitals are oriented in between x and y axis. So non-axial orbitals in this manner. Okay, it is a clear explanation, clear pictorial representation of d orbitals in the cube. So based on the ligand, how it is been approaching in different ways or different corners of the cube, the splitting of the d orbitals will be done. Let's see the axial orbitals. We know that it is a dz square orbital, that is along the z-axis. Along the z-axis, the orbital is oriented. So that is the reason it is dz square orbital. Then dx square minus y square orbitals are oriented along the x-axis. This is x-axis. This is x-axis. This is y-axis. This is z-axis. So along this x and y-axis, this dx square minus y square orbitals are oriented. So when we consider these orbital structures, when the ligands approaching towards the central metal atom will be at the center of the cube. Here the central metal atom should be there. So towards the central metal atom, if the ligands are coming by the corners of the cube or by the axis of the cube, depending on that, the d orbital splitting will be done. Remember, in crystal field theory, there is no sharing of or pairing of electrons is being considered. only the electrostatic force is being considered. So let's consider the splitting of d orbitals. As we discussed, the d orbitals, degenerative orbitals in their nature, but depending on the approaching of the ligand, these d orbitals will split. How these d orbitals will split? Let's take this is a d orbital. Okay, at the ground state, it will be all the orbitals are degenerated. When the spherical crystal field is created, that means the ligands or the electrostatic forces to these d orbitals are in all the directions of a sphere. Consider a cube. A cube overcome by the or overlap or in a sphere. So in this cube, all the points are equally affected by the sphere. A sphere is an electrostatic force which is coming towards the center metal atom. So in this case, no splitting, no degeneracy will be happen, but the degeneracy will be retained, but it will show at the higher energy level. So it is d orbital in free metal or metal ion. D orbital when it is being influenced by the spherical field, spherical electrostatic field. So the energy is somewhat more than the free orbital. Then here the splitting will be done. Splitting will be done in such a way that the axial orbitals, that is dx square minus dy square and dz square, and non-axial, that is dxy, dyz, dxz. In this way it will split. This group is called as EG group and this group is called as T2G group. In a group theory, it is mentioned in this way. EG group is a axial orbitals, that is 2 in number, and T2G is a non-axial that has 3 orbitals, that is dxy, dyz, dzx. So, this is dxz. So, the splitting will be done in this way. EG and T2G will separate depending on the approaching of the ligand. So, this splitting is clearly explained in the crystal field theory. After the splitting is been done, then the pairing of the electrons will be done. There is no external or there is no ligand electrons will pair with the d orbitals. There is no overlap is being seen. Before going for the splitting of octahedral, let's see the splitting of d orbitals in tetrahedral complexes. So before understanding how the splitting has been done, let's see the structure of tetrahedral. This is the tetrahedral structure. You can see this is the cube. This is the cube. The corners of the cube are in this way. And you can consider one of the axis as x-axis, one of the axis as y-axis, and one of the axis as z-axis. So in this cube, 1, 2, 3, 4. 4 corners of the cube are being occupied by the ligands in the tetrahedral splitting. So the approaching of ends will be in this way. So it is towards the axial, so the approaching of the ligands in the tetrahedral geometry is towards these points. So whatever the orbitals are there in the approaching areas of the ligands, those orbitals will exert the higher energy in the d orbital. That means the splitting will be done in such a way that along the axis or in between the axis, if the ligands are coming approaching towards the metal atom, the the orbitals which are there in between will show the higher energy level. So the T2G and EG groups will split in such a way. Let's see the splitting. This is the d orbital. D orbital, the free metal ion. This is the energy. Then this is the force influenced spherical force, spherical electrostatic force influenced. So the spherical field has been created. So the energy is increased. From here, it will split into the non-axial and the axial. That means this is EG, this is T2G. So EG will show the lesser energy than the degenerated d orbitals, and T2G will show the higher energy than the degenerated d orbitals. Why it is showing the higher energy? Because the ligands are approaching in this direction. The non-axial plane will approach in the non-axial plane. The ligands will approach in the non-axial plane, so that the T2G energy levels will increase. The EG energy levels will decrease further than the degenerated orbitals. That is called as the barycenter. Barycenter is the energy level with the spherical field. From the barycenter, the EG, the energy level will decrease, and T2G energy level will increase. And it is said that it is 2 by 5 of delta, it is 3 by 5 of delta. Delta is the crystal field stabilization energy. For tetrahedral complex, it is delta T means tetrahedral crystal field stabilization energy. So because it is going upwards, because we have 5 orbitals, so 2 by 5 of the delta T will be increased for the T2G, and 3 by 5 of the delta T will be decreased to the downwards than the barycenter. So this splitting of orbitals will purely depends on how the ligand is. How the ligand is. Because the ligands have strong field and weak field ligands. Weak field ligands and strong field ligands. Strong field ligands are those ligands which will split the d orbitals in such a way that strong field ligands will split the d orbitals in such a way that the maximum splitting should be done, and the weak field ligands will split the d orbitals, or sometimes they cannot able to split the d orbitals, and the energy between these two will decreases. So now we will write the spectrochemical series of these ligands. So from the weak field I will start, that is I minus, Br minus, S minus 2, Cl minus, NO3 minus, F minus, OH minus, ET, ethyl alcohol, ETOH, and oxalate, the neutral atom, the neutral molecule, and H2O, the neutral molecule, and NCS, and EDTA, and NH3. NH3 and pyridine will show the equal kind of splitting field, or strong field or weak field energy. And then EN, then dipyridine, then orthophenolphthalein, then NO2 minus, Cn minus, and CO. So from here, I minus, Br minus, and S2 minus and Cl minus are the weak field ligands, and they will fail to split the d orbitals. And CO, Cn minus, and NO2 minus very strongly they will split the energy levels of T2G and EG. Now we will see the strong field and the weak field ligands, how they are splitting the d orbitals. The crystal field splitting in octahedral complexes. Before going for the octahedral splitting, let's see how the octahedral structure will look like. This is the octahedral structure. So at the center, the metal atom will be there. The metal ion will be there. And to that, all these points are the ligands. The ligands will be in this way, they are arranged, and at the center, the metal atom will be there. So in a cube, if you consider all these will approach through the axis, not through the corners of the cube. Try to draw the square here. When we draw a cube here, see, these are approaching through the axis, not through the corners. And even these two will go through the downside and upside corner or axis of the cube. So that is the reason in octahedral, the EG group, the axial orbitals will exert the more energy from the ligands. So the splitting will be done in such a way that the EG group, the axial orbitals of the d orbitals will show the higher energy level than the T2G. This is quite reverse of the tetrahedral complexes. In a tetrahedral complex, we have seen the T2G group will exert the more energy because through the complex, through the geometry of the tetrahedral, the non-axial places are the approaching points for the ligands. So here consider the d orbitals, the free state, then the energy is increased, the average energy of d orbitals in a spherical field. Then the splitting will be done in this way. This is the increasing energy, and this is the barycenter or average energy. So this is T2G group and this is EG group. So the axial orbitals, that is dz square and dx square minus y square, will exert more energy or more electrostatic force from the ligands. So that is the reason they will show the higher energy level. And this dxy, dyz and dzx will show lesser energy because the ligands are not approaching by this non-axial plane. So now we will see how the splitting will be done with respect to the spectrochemical series, that is weak field energy, weak field ligands and strong field ligands, how they are splitting the d orbitals we will see now. Okay, see, you can see this for the d1, when the d orbital, for the d1, that is the example titanium +3 ion with the high spin complexes, that is strong field. High spin means that is strong field ligands. This is low spin means weak field ligands. So the splitting will be done in octahedral in such a way that when titanium +3 is being taken, the T2G will be filled with the 1 electron. That is the energy associated, the crystal field stabilization energy associated with this particular electron is -2/5 delta. So here crystal field splitting, in this crystal field splitting, here the energy difference, here it is 2/5 delta O and this is 3/5 delta O. The delta O means crystal field stabilization energy of octahedral complex. The O indicates the octahedral complex. Now we will see how the crystal field splitting is been done for the various electronic configuration of d orbitals. Okay, when the d1 is present, that is, let's take here the example of titanium plus 3. When the titanium plus 3, d orbital will bear only one electron, and the splitting will be done in this way. T2g being a lower energy level, the electron will be filled here first. Okay, and same case with the weak field ligands, that is high spin. Then the d2, when the d orbital has 2 electrons, then the splitting will be done in this way, that is the titanium plus 2 and the vanadium plus 3. When these two are there, then the splitting will be done almost the same for the weak field and strong field ligands. And D3, with the D3, it is also the same, and the examples here are vanadium plus 2 and chromium plus 3. These ions will split in the same way even for the strong field ligands and the weak field ligands. And here the 12 dq, the delta q. See, this is the energy level which is coming for the 2 by 5. This is 4 by 5. Okay, 2 by 5 means it is 0.4. I'll write here, it is 2 by 5, that is 0.4 of delta O. Okay, the delta O is written in the dq form by simply removing the decimals, that is multiplied by the 10. So here it is 4 by 5, and here 12. It is 6 by 5, that is 1.2. Okay, in this way all are written. So for the D4 electronic configuration, the T2G4 will split in a different way with the strong field ligand and with the weak field ligand, because D24, in the strong field ligand, the energy gap between T2G to EG will be very high, so the electrons will be filled here itself. Okay, but whereas in case of weak field ligands, the energy gap will be maintained in such a way, so the electrons will be filled accordingly. That means all are half filled. Then for the strong field ligands, the T2G, the D5 T2G will be filled in this way. The T2G will be filled with the 5 electrons, but whereas here T2G will be half filled and EG also half filled. So here the number of unpaired electrons will be 5. Here the number of unpaired electrons for each and every time, it is 1, it is 2, it is 2, it is 3, it is 3. Here it is 2, here it is 4. Here the number of unpaired electrons is 1, here the number of unpaired electrons is 5. Again, here if you consider the number of unpaired electrons are for the D6 electronic configuration is 0. And for the number of unpaired electrons in the weak field ligand is T2G 4 and EG 2. That means 4. Okay, so here the number of unpaired electrons will become 1, and here the number of unpaired electrons will become 3 again. Here the number of unpaired electrons when the D8 configuration, that is T2G, will be completely filled and EG will be half filled. So it will be 2. So number of unpaired electrons here is also 2. Number of unpaired electrons in D9 electronic configuration will be 1, and here also it is 1. So here the number of unpaired electrons is 0, and here the number of unpaired electrons is 0. Accordingly, you can check now. We can see how the crystal field stabilization energy is related with the number of unpaired electrons. So if the unpaired electron is 1, then the crystal field stabilization energy is 4 dq. 2, it is 8 dq. 3, it is 12 dq. It is 2, it will become 16, and here it will become 6 dq. Okay, so for the D5 electronic configuration, it is 1 and it is 5. Likewise, all the strong field and the weak field energy levels with the number of unpaired electrons is being shown. Now We will see the examples of the D3, D4, D5 configuration. D4 electronic configuration, it is chromium plus 2, it is manganese plus 3, manganese plus 2, then iron plus 3. Here it is D6, iron plus 2, cobalt plus 3. For the D7, cobalt plus 2 and nickel plus 3. D8, nickel plus 2, platinum plus 2. For the D9, it is copper plus 2. For the D10, it is zinc plus 2. These are the examples. Okay, so in this way, the crystal field splitting of the octahedral complexes are being explained.